A spacetime with no massive bodies has no gravity. So in Newtonian language, there are no gravitational forces. In general relativity language, we say there's no curvature. Okay? With no curvature, the spacetime is referred to as flat. And this is the spacetime of special relativity. All right, we know that in Minkowski coordinates, the line element for a flat spacetime of special relativity is minus dt squared plus dx squared plus dy squared plus dz squared. Of course, we can also express this in other coordinate systems, for example, in Rendler coordinates. The line element reads minus rho squared d tau squared plus d rho squared plus d c squared plus d zeta squared. So these line elements represent the same spacetime. It's just a flat spacetime of special relativity, just expressed in different coordinates. For simplicity, let's drop two of the dimensions. So let's drop the y and z directions and just consider flat two-dimensional space-time in Minkowski coordinates. So the line element reads minus dt squared plus dx squared. Now, one thing that we know about space-times is they have a mixture of plus and minus signs in the line element, and that means that ds squared can be either positive, negative, or zero. So let's draw a space-time diagram here. All right, for ds squared equals 0, that means dt by dx, or dx by dt, whichever way you want to write it, is plus or minus 1. So these are the events that are light-like separated, or sometimes we call them null separated, and they're connected by a light ray. So from here we see that light rays travel along 45 degrees in this diagram, along curves of slope plus or minus 1. So if I can draw this at about 45 degrees, there's one light ray, here's another light ray. So here's light at 45 degrees. So if we consider now this event at the crossing of the light rays, we see that the light rays divide the space-time up into 4 regions. And other events that are, say, in the upper wedge, these events are time-like separated. Okay, that's the case in which ds squared is negative. And you can see that fairly easily, and from the line element you can see the way I've drawn these 2 points that dt is relatively larger than dx. So the minus sign term here is going to dominate and give us a ds squared that's negative. On the other hand, a point here, if we look at the separation between these 2 events, these are space-like separated. That's the case ds squared is positive. And you can see that in the line element as well. In this case, these 2 events are separated by a relatively large dx and a relatively small dt, so the plus sign here dominates and gives us a positive ds squared. So points that are in this upper wedge are considered to be in the future of this event. So this is the future region. And it's the future in the sense that this event can have a causal influence on any event within this future region. And that includes the boundary here, these light curves. Okay? So we could connect these two events, say, by a car traveling from here to here. We could probably walk from here to here. To connect an event from here to here, we need a light ray. But in any case, we can always connect these in a causal sense, so we can carry information from this point to any of these points into the future. And similarly, this lower wedge is the past of this event. So any event down here, including events along the boundary, any events in this region can have a causal influence on this event here. On the other hand, if you look at these two events, they're space-like related or space-like separated. They can't have any causal influence on one another. Right? In order for this event to have an effect on this event, there would have to be information traveling faster than the speed of light. So these wedges here, these light curves, form the boundary of where information can flow. This upper wedge is referred to as the future light cone, and this is the past light cone. And the reason these are referred to as cones is because if we try to draw this picture in two space and one time dimension, so if I add a y direction here, then this region of the future region becomes the interior of a cone, and the past is the interior of this cone. This region is usually referred to as the future light cone, and we draw it like this. And this is the past light cone. And the reason we draw these as cones is because if you imagine this same construction in two space and one time dimension, so let's add a y-axis here and add a plus dy squared to the line element, then this cone would be the surface of light rays emanating from this event. So imagine this event to be, say, a firecracker explodes and gives off a flash of light. That flash of light would be the wave front. The light wave front would be an expanding circle, expanding into the future, and that's what this cone represents. And similarly, this past cone is the wave front of light that is converging onto this event. Of course, we really live in three space and one time dimension, so really what the light cone is the future light cone is an expanding wave front of a spherical wave front expanding out from a single point. Now let's turn our attention to geodesics in space-time. A Timelike geodesic is a curve in space-time that extremizes the proper time between events. So let me remind you that when we have two nearby events that are timelike separated, then ds squared is negative. So we define d tau squared as minus ds squared, which is positive. And that's d tau is the proper time separation between two nearby events. Now if we have two events that are not close to one another, the proper time is just obtained by integrating d tau. So this is the proper time between events, and this is what we look to extremize for a time-like geodesic. Now, time-like geodesic, as an important physical interpretation, it's the world line or the path taken by an unaccelerated particle observer. So this the world line of an unaccelerated particle or observer. So another way to say this is it's the world line of a freely falling particle or observer. Freely falling particle or observer. Okay, so what do we mean by freely falling? Okay, for a particle to be in free fall, we mean that it's uninfluenced by any external forces. So, in other words, no contact forces, no electromagnetic forces, any other physical forces, say strong or weak nuclear forces. Of course, contact forces are primarily electromagnetic forces at the microscopic level. Okay, notice in this list of forces that we're excluding for a body to be in free fall, I haven't included gravitational forces, because remember, gravitational forces are fictitious. So I'll put the word forces in quotes here. So I don't need to add that to this list. An example of a body that's in free fall near the surface of the Earth is, say, a pencil that you drop. So here's a pencil, drop the pencil. While the pencil is falling, it's in free fall. So it's not being acted on by any of these forces. So it's unaccelerated. And it's following a time-like geodesic. An example of a body that's not in free fall is you standing on the surface of the Earth. Okay, you're being acted on by a contact force with the floor, and that's causing you to accelerate radially outward from the center of the Earth. Later on, when we write down the line element for a massive spherical body like the Earth, we'll be able to actually compute the acceleration of a body or a person standing on the surface of the Earth and see that it's not zero. Okay, let's compute the time-like geodesics for flat two-dimensional space-time in Minkowski coordinates. So this is line element minus dt squared plus dx squared. And so we'll consider a curve, a general curve, t of lambda, x of lambda, and we'll assume that this curve is time-like. In other words, every pair of nearby points along the curve are time-like related. So we define d tau squared to be minus ds squared. That's dt squared minus dx squared. And we can now write dt as dt d lambda times d lambda. So this is, why don't we call dt d lambda t dot. So dx squared would then become x dot d lambda squared. So here the notation is t dot is dt d lambda, x dot is dx d lambda. Okay, so taking the square root of both sides, d tau is t dot squared minus x dot squared times d lambda. And then the proper time between two points is just given by the integral of d tau. So that's integral of square root of t dot squared minus x dot squared d lambda, integrating from some initial point given the parameter value lambda 1 and some final event with parameter value lambda 2. All right, so we now want to extremize this expression. And the procedure should be familiar from Lagrangian mechanics. We vary this quantity and set the variation equal to 0. So first varying it, we have integral from lambda 1 to lambda 2. This is 1/2 1 over the square root of t dot squared minus x dot squared. And now dipping to the inside of the square root, this should be squared here. We have 2 t dot delta t dot minus 2 x dot delta x dot. All of that times d lambda. Okay, the 2's cancel the 1/2s there. And what we need to do is now integrate by parts to remove the dots from delta t and delta x. And when we integrate by parts, of course, we pick up a minus sign. So this would be minus d by d lambda of t dot over the square root of t dot squared minus x dot squared times delta t minus, actually plus, because there's already a minus sign here, plus d by d lambda x dot divided by the square root of t dot squared minus x dot squared delta x d lambda. Okay, now setting delta tau equal to 0 for arbitrary delta t and arbitrary delta x, this can only be 0 if the coefficients of delta t and delta x both vanish. So this tells us that d by d lambda of t dot over the square root of t dot squared minus x dot squared is 0, and likewise d by d lambda of x dot divided by square root of t dot squared minus x dot squared is 0. So these equations are now pretty easy to solve. This tells us that t dot over the square root of t dot squared minus x dot squared is a constant. This equation tells us that x dot divided by the square root is equal to a constant. So dividing these two equations, we see that x dot over t dot is a constant. So dx dt is a constant. So these are just straight lines in the space-time diagram. So what this calculation shows is that if we have two time-like related events, so these are time-like related because this event is in the future light cone of this event, then the extremum of proper time between those events is given by a straight line. So there's one time-like geodesic, and of course here's another time-like geodesic, and so forth. And all of these geodesics are time-like, so they have a slope of less than 45 degrees in this diagram. And by the way, we could also consider space-like geodesics, so we can pick 2 points that are space-like related and ask for what is the extremum of s, the integral of ds, between these points. And we would find in that case as well, the calculation is almost identical, that these space-like geodesics, as they're called, are just straight lines in this simple case of flat two-dimensional Minkowski space-time. But these geodesics aren't really of much physical interest. It's really the Timelike geodesics that are physically interesting because they represent the paths of freely falling observers or freely falling objects. Now I'd like to spend some time deriving some familiar results from special relativity. Special relativity. As warm-up, let's just consider the following problem. We have an observer moving along a curve x equal vt in this space-time diagram. And we can consider another observer just moving right along the t-axis. So this is the observer moving along the line x equals 0. So the question I'd like to ask, and the answer is, what is the velocity of this observer, or this could be a particle, as seen by this observer who stays at rest at x equals 0? Okay, well, for this observer at x equals 0, the way that this observer determines the velocity of this particle is by considering an event here and asking, well, actually considering two events. Let's also consider the event in which the observer and the particle cross right at the origin. Okay, so the observer asks, what is the time elapsed between this event and this event, and what is the distance of this event from me? Okay, and take that distance divided by that time, that gives the velocity. All right, for this observer, the set of events that are simultaneous with this event are represented by a horizontal line in this space-time diagram, right? This it's the set of events that have the slope that's the inverse of the slope of the observer. All right, so this observer will assign a time to this event, which is the same as this time of this event right here on the observer's world line. So first of all, what is the time elapsed on this observer's clock between this event and this event? All right, that's a proper time, integral of d tau, between these two events, using the line element for flat two-dimensional space. Space-time, we have square root of minus dt squared minus dx squared. But the change in x between these two events is 0, right? So this is just the integral of dt, which is just t. So the t values along this coordinate axis are measuring proper time for this observer. And actually, just for notational consistency later on, let me call this delta tau. So this is the proper time interval between this event and this event. It's just the t value of this event. Okay? And likewise, if we ask for the proper distance between these two events, okay, we'll call that delta s. That's just the integral of minus dt squared plus dx squared. But because t is not changing from this event to this event, dt squared is 0, and this is just the integral of dx, or in other words, x. So the x coordinate values in the space-time diagram measure proper distance for this observer who stays at rest at x equals 0. All right, so the speed or velocity of this particle as observed by this observer is then just delta s over delta tau. That's just x over t, which, because x and t are related by x equal vt, this is just v. All right, so this observer sees this particle moving at speed v. No surprise there. Now it's an interesting exercise to turn the reasoning around. Let's consider the same picture. This is the x-axis, this is the t-axis. We have the two observers, one moving along the curve x equal vt and the other moving straight up the t-axis. So this is the curve x equals 0. And now let's ask, what speed does this observer see for this observer, or this particle? We'll call this a particle now. So what speed does the x equal vt observer assign to the x equals 0 particle? All right, we can compute this the same way as by using the same reasoning as we did before. Let's pick an event on the particle world line. And just to be specific, let's give this event the coordinates, well, the x coordinate is 0, of course, and we'll let the t coordinate be capital T. Now this observer looks to find an event on his own world line that's simultaneous with this event, and the events that are simultaneous to this observer lie along a curve, or a line, which has slope equal 1 over v. All right, so this line is given by the equation x equal 1 over v times t, but actually that's not correct because this line is shifted up from the origin. It has a y-intercept, so to speak. So this is actually x equal 1 over v times t minus capital T. Gives the equation for this line. All right, so what are the coordinates of this event? Well, the coordinates of that event are given by the intersection of this line of simultaneity, with the world line of this observer. So we need to simultaneously solve the equation x equal vt and this equation. All right, so let's do that. If we set the right-hand sides of those equations equal to one another, since x, the left-hand sides are both x, we have this equation. And now simplifying, we have t minus capital T equals v squared t, or 1 minus v squared times little t is equal to capital T, which tells us that little t, the coordinate t coordinate value of this event, is equal to capital T divided by 1 minus v squared. And now I'm going to introduce the standard notation gamma equals 1 over the square root of 1 minus v squared, familiar from special relativity. All right, so with that notation then, t is equal to gamma squared times big T. So that's the t coordinate value of this event, and the x coordinate of this event is just v times little t. So that would be gamma squared v times capital T. All right, so now that we know the coordinates of this event, we can work out the time as seen by this observer's clock between this origin event and this event that we just worked out the coordinates of. We can work out the proper time as well as the proper distance between these events. So first of all, what is the proper time between these events? We can work that out by integrating the line element along this this curve, this line segment from this event to this event. And let me first do that the fancy way. Let's parameterize that curve. So the parameterized curve can be expressed as t of lambda equals gamma squared t times lambda, x of lambda equals gamma squared VT, capital T, times lambda, where the parameter lambda ranges from 0 to 1. Okay, that takes us from the origin event, at lambda equals 0, to this event when lambda equals 1. And so now the proper time interval, we call it delta tau. That's the integral of d tau. It's the integral of the square root of t dot squared minus x dot squared d lambda from lambda equals 0 to 1. And where dot denotes differentiation with respect to lambda. And now t dot is just gamma squared times capital T, and that's squared. And x dot is gamma squared V times capital T. Now, of course, this integral over lambda is just going to give us a factor of 1. So this is equal to gamma squared T quantity squared minus gamma squared VT quantity squared. We can factor out a common factor of gamma squared T from these two terms and bring it out under the square root. And then what we're left with under the square root is 1 minus V squared. Okay? Square root of 1 minus V squared is 1 over gamma. So this is gamma times capital T. So that's the proper time between this event and this event, as seen by, which is the time on the clock of the observer who's traveling along this x equal vt curve. Now, of course, in this case, when we're dealing with flat space-time and Minkowski coordinates, we don't really have to be so fancy as to parameterize the curve. This result, delta tau, it's just what we get if we compute the change in the t-coordinate squared minus the change in the x-coordinate squared, square rooted. Right? The change in the t-coordinate is just gamma squared times capital T. The change in the x-coordinate is gamma squared V times capital T. And now that, well, that's the same expression we have here, so this, of course, simplifies to gamma T. So we can use this fact in future calculations to simplify the calculation of proper times and proper distances by just computing the change in the coordinate time and coordinate distance and using the line element in this way. All right, so this is the result for the proper time between these two events. Now, what is the proper distance between this event and this event? All right, the proper distance, that's just computed as minus delta t squared plus delta x squared, square rooted. So the change in the t coordinate between these two events is what? Well, the t coordinate of this event is gamma squared times capital T, and the t coordinate of this event is just capital T. So that's gamma squared T minus T quantity squared plus delta x. The x coordinate of this event is gamma squared V times capital T. The x coordinate of this event is 0. Okay, so that's the proper time or proper distance between the two events. Let's simplify this. All right, we have here minus gamma squared minus 1 quantity squared times capital T squared plus gamma to the fourth V squared times capital T squared. Okay, let's factor out the capital T. And let's also multiply out this the square of this gamma squared minus 1. So this would be minus gamma to the fourth plus 2 gamma squared minus 1. And then from this term we have plus gamma to the fourth V squared. And here's the factor of T out from under the square root. All right, so this is, let's combine these two terms with the factor of gamma to the fourth. So this is minus gamma to the fourth times 1 minus v squared plus 2 gamma squared minus 1, all times capital T. Now 1 minus v squared is 1 over gamma squared. So this is minus gamma squared plus 2 gamma squared minus 1 times capital T, which simplifies to gamma squared minus 1 times capital T. And we can further simplify that by just using the definition of gamma. So the definition of gamma is 1 over the square root of 1 minus v squared. So gamma squared is 1 over 1 minus v squared. Now we subtract 1. Let's write that as 1 minus v squared divided by 1 minus v squared. Now you can see that this 1 cancels this 1, minus sign and a minus sign gives us a plus sign. So this is the square root of v squared over 1 minus v squared times capital T, which is equal to bringing the v outside, and the 1 over square root of 1 minus v squared is gamma. So this is gamma v times T. So this is the proper distance between events as seen by the observer moving along this x equal vt world line. So again, what we're computing is we want to compute the speed of this particle as seen by this observer. So we now have the time interval, it's gamma times capital T, and we have now the space interval. So the velocity of the particle as seen by the observer is delta s over delta tau, which is gamma vt divided by gamma t, which is just v. All right, so just as expected, the observer sees the particle moving with speed v, or if you want to be more precise, we could have taken the negative square root here and called this minus v for the velocity. Right? In general, if one observer sees another observer moving at speed v, then the second observer also sees the first observer is moving at speed v, or velocity minus v. Now let's take a look at length contraction. This is the well-known result from special relativity that moving rods are shorter than they are if they're not moving. All right, so let's consider a rod moving with speed v. So here's my space-time diagram. And I'm going to consider an observer who's sitting at rest at x equals 0, so the observer is moving right up the t-axis. So this is my observer. And the rod looks like this. So this is the left end of the rod, and we'll arrange for the left end of the rod to pass right through the origin. And here's the right end of the rod. Left and right ends of the rod. So these are the world lines of the two ends of the rod. And we want to determine how long this observer thinks these rods are. And we'll also consider an observer who's riding along with the rod, say right at the left end of the rod, how long that observer thinks the rod is. All right, so this the left end follows a curve x equal vt, and the right end follows a curve that's just displaced by some amount, some constant amount I'll call L sub m. Okay, and let me explain why I'm using this notation L sub m for the displacement. So L sub m is just this distance from this event to this event, right? It's just the x coordinate value of this event. And recall that this observer that sits at x equals 0, for that observer, events right along the x-axis are all simultaneous. So if this observer wants to determine the length of the rod, what this person can do is to check the location of left and right ends at the same time, simultaneous with one another, and then see what the proper distance is between those events. So just as the left end crosses the origin, this observer says, well, this is where the right end is at that same time. So this is a coordinate distance LM away, and for this observer, that's also the proper distance. So for this observer, the proper length, the length of the rod as seen by this observer is L sub m, and I'm using the subscript m to refer to moving. So in other words, this is the length of the moving rod as seen by this observer who's at rest at x equals 0. Now what is the proper length of the rod? The proper length of the rod is the length of the rod as seen by an observer who's moving along with the rod. So in other words, an observer for whom the rod is at rest. So if we consider an observer moving along with the left end, for that observer, the set of events that are simultaneous with, say, the origin are the events along this dashed line segment. So this is the line segment x equal 1 over v times t. Right? So for the proper length is given by the line element. It's the proper distance between this event and this event. So the coordinates of this event, let's work that out. This event lies at the intersection of this line and this line. So both of these equations have x on the left-hand side, so let's set the right-hand sides equal to one another. That's 1 over vt equals vt plus lm. So simplifying this, we have t equals v squared t plus v times lm, which tells us that 1 minus v squared times t is equal to v lm, or t is equal to v times lm divided by 1 minus v squared, but that's gamma squared. All right, so that's the t coordinate of this event, and the x coordinate is just 1 over v times the t coordinate. So the x coordinate is just gamma squared times lm. All right, now what is the proper length of this line segment? Okay, well that's delta s is minus delta t squared plus delta x squared, and delta t is gamma squared v lm minus, well, since our second event is at the origin, that just has t equals 0. That's minus 0 plus delta x, that's gamma squared lm minus 0, again squared. All right, so simplifying this, we have gamma squared v lm quantity squared minus gamma squared lm quantity squared. You have a common term, gamma squared lm, in both of these terms under the square root, so let's factor that out. And under the square root, we're left with, and I see here I have the minus signs reversed. We should have a minus sign here and a plus sign here, minus sign here, plus sign here. Right, so this is 1 minus v squared under the square root. That, of course, is 1 over gamma. So our result for delta s is gamma times lm. All right, so this is delta s. This is the proper length of the rod. All right, so of course we can turn this around and write the length of the moving rod is 1 over gamma times the proper length. So moving rods are shorter. Gamma, remember, is always greater than 1. So we're dividing the proper length by something larger than 1. We get a smaller length. So moving rods are indeed shorter. Now, an interesting calculation that you should try is to turn this around and let the rod be at rest in the TX coordinate system. So here's the left end of the rod, here's the right end of the rod. And let the observer be moving with speed v in this coordinate system. Okay, and you can work out the length of the rod as seen by this observer, and of course you should find the same result, that the length of the rod as seen by the observer for whom the rod is moving is 1 over gamma times the proper length of the rod. Now let's take a look at time dilation. This is the well-known special relativistic effect that moving clocks run slow. All right, we can set up the calculation as follows. Here's my space-time diagram, and here's my clock, which is moving relative to an observer who's at rest. So here's my observer traveling along x equals 0, and here's the clock moving along x equal vt. Now the clock ticks, all right, so we'll arrange for one clock tick to occur right at the origin as the clock passes the observer. Here's another clock tick preceding that one. Here's a later clock tick. Okay, so each time the clock ticks, it's an event. Now, the first question is, what is the time between clock ticks as seen by this observer? Well, for this observer, the event along the observer's world line that's simultaneous with this clock tick is this event right here. So all of these events along this horizontal line are simultaneous as seen by this observer, because this line has the inverse slope of the observer's world line. So let's call the t-coordinate of this event capital T sub m. This is now this is actually the proper time between these two events, which is the time seen on the clock by the stationary observer, the observer at x equals 0. So this coordinate t sub m, this coordinate time t sub m, is the same as the proper time interval here. So what is the proper time interval between these events? That's the time seen on the clock by the clock itself. All right, well, we can work that out. The proper time interval here, let's call it t sub proper, t sub p for proper. Okay, that is the square root of delta t squared, little t squared, minus delta x squared. All right, now the t coordinate of this event is t sub m, and the t coordinate of this event is 0, minus the x coordinate of this event is just v times t sub m, and of course the x coordinate of the origin is 0. All right, so this is square root of tm squared minus v squared tm squared. Factor out the tm, and we're left with 1 minus v squared under the square root, and that's just 1 over gamma. All right, so we can turn this around. Of course, this says tm is equal to gamma times the proper time. Now, how do we interpret this? Well, what this is telling us is that whatever the time interval is, the proper time is measured on the clock. Let's say the clock measures 1 second between these events. The time is seen by the observer who's at rest in this space-time diagram is larger than that. It's, say, 2 seconds. So this observer is looking at this clock as it's moving past and saying 2 seconds have passed between these ticks, but yet the clock only registers 1 second as having passed. So the moving clock is running slow. It's an interesting exercise to turn this around and draw the space-time diagram with the clock at rest and the observer moving. So let the clock run along x equals 0. And the observer move along the world line x equal vt. And do the same calculation. Find the time that the observer sees between ticks. Compare that to the proper time. And you, of course, should find the same result. The moving clocks run slow. The moving time is gamma times the proper time. Now let's consider the twin paradox. All right, we have twins. One twin stays at home. So that twin just sits at x equals 0 in our Minkowski coordinate system. The other twin leaves, circles around Alpha Centauri, and returns. And we find that the twin who travels ages less than the twin that stays at home. All right, how do we see that? Well, for the twin who stays at home, the proper time along this curve, so we'll call that t home, is just, well, it's always just the integral of square root of dt squared minus dx squared. Okay, so this twin stays at home, so dx is 0, so this is just, of course, integral dt. So it's just the coordinate time interval between these two events, right? For the traveling twin, well, whatever this world line is, we could parameterize it if you like. Some x of lambda, t of lambda. This is dt squared minus dx squared. In this case, dx squared, or dx itself, is not 0. Okay, so whatever it is, this minus dx squared is always subtracting from something from the dt squared. So this is always less than integral dt, which is, of course, the t at home. So we see that no matter what dx is, no matter what the details of this world line are, that the traveling twin has a smaller proper time between this event and this event than the stay-at-home twin. So the stay-at-home twin ages more than the traveling twin. Now, this is sometimes referred to as a paradox because one might say, well, what if I had a different coordinate system in which the traveling twin was at some constant x value and this twin had some non-trivial world line, some non-trivial t of lambda, x of lambda. Wouldn't it be the other way around, that we would find that the traveling twin ages more than the stay-at-home twin? And the answer is, of course, no, because if you can do that, you can change coordinates to a system in which the traveling twin is at rest in the sense that he or she stays at a constant spatial coordinate. But in those coordinates, the line element is no longer the Minkowski line element. It's no longer dt squared minus dx squared. So when you work out the proper times between events along the two different world lines, you get the same result. It doesn't matter what coordinate system you use. And of course, physically, the distinction between these two twins is the stay-at-home twin travels along the geodesic, whereas the traveling twin does not. So that's what breaks the symmetry between these two world lines.